Alright, welcome back to another AQA A-level chemistry video. Today I'm going to be doing a video starting on the inorganic year 2 unit. I'll be doing a video today specializing in period 3 elements and oxides. That's the topic that we're going to be doing today, period 3 elements and oxides. And yes, I know it's been a long time. I've been out for quite a bit. I need to take some time off. But I'm not gonna go too much into that. I'll definitely say I'll finish off the content before exams. I probably won't finish off the exam questions before exams, but I'll definitely finish off uh year two. But the rest of the content is just year two inorganic chemistry. I've done everything else, and as well from the comment section, people have been asking the majority of the questions in relation to inorganic year two inorganic chemistry. I think that's what people are already on or finished by this point in time. Now you probably would have finished. You should have finished the content by now, and if you haven't, you're probably still on inorganic chemistry. And I'll go through this right now. If and again, if you have any questions relating to inorganic chemistry or just any questions in general, you can ask me in the comment section. If I can't answer it, I'll try and direct you to a video that will probably give you the best information. Again, I'm not Superman. Well, Superman's probably not even that smart for me. I don't even care. I'm not, you know, the smartest individual, but I can say that I can try and help out. Now, I will go straight into video. I'm not going to waffle on for too long, but what I will say is that we're now going to be starting year two in organic chemistry. But like year one in organic chemistry, it's a very quick topic. But don't get confused that because it's a quick unit to get through, that it's an easy unit to get through. It's quite I didn't struggle with it too much, but then again, I'm speaking as someone that's already done my exams. But I definitely say it's quite hard to get your head around, and some people that I know get very, they say this is the most confusing unit out of all of them. And it's very important that you get this section right, because in the exams, a lot of the content is so heavily focused on the terminology that you understand from year two in organic chemistry. So without further ado, I'll get straight into the video. I'll probably leave a timestamp in relation to if you want to just go straight to certain parts of the video. But yeah, so reactions of the third period with water. The third period elements show many interesting reactions with water. Now, group we understand that groups are going down the periodic table, and periods go across the periodic table. And the one that they would like to focus on the most is period 3. Period 3 being this one here. So that's one they like to focus on the most. Now, I want to make it very clear that I have seen examples in the exam where they have asked for period 2, where they have asked questions in relation to period 2, which is the one just above it. Now, don't get disheartened by this. Don't get confused by it. Don't get like, oh, I don't know what to do. I didn't study about period 2 oxides. Oh, I didn't study about period 2 reactions. I'll go through period 3 today, but just like in year 1 in organic chemistry, what you need to understand is that reactions going down the periodic table, the number of valence electrons stay the same. The electron is added to a new energy level, yes, going down the table. Yes, the increasing number of shells that we have, but the valence number of electrons is the same. So we're expecting the same type of overall reaction. That's what you need to think about. Going up or down a group is the same thing, right? I mean, the I'm saying that the valence number of electrons is the same. Obviously, if you're going down the periodic table, then you're increasing the number of shells. But the most important thing is that the elements in a group have the same valence electron shell. Whereas when you're going across a period, it's different now, where your valence number of electron. And when I say valence, if you don't know what I mean by valence electron, it's the amount of electrons you have on your outermost shell, right? So in group 5, right, there's 5 electrons on the outermost shell. Now the number of electrons that you have overall is different, or is increasing as you go down the periodic table, because we're increasing the number of shells, but the amount of electrons that we have on that outermost shell is 5. And one here, if we're going for this group here for group 1, sodium has 1 electron in its outermost shell, potassium has 1 electron in its outermost shell, and that's what I mean by the reaction isn't the same. Whereas when you got the reaction is the same, roughly the same type of reaction that you see, a chemical reaction. Physical reaction may be different, but the chemical reactions you should expect them to be the same. Whereas when you're going across a period, you see different types of reactions because the valence number of electrons are different. Uh, so you'd expect different types of reactions. The size of the physical properties are also different. But if we're talking about chemical reactions here in relation to period 2 and 3, they should have the same as you're going across the group, as you're going across the period. You'd expect the same type of reaction for that group. Now, what do I mean by this? So we know from period 1 that there's a difference in the ionization energy between phosphorus and sulfur because of the electron shielding, right? Sulfur has paired up. Let me just change colors. Uh, Sulfur has a paired number of electrons. Is it phosphorus? No, it's sulfur, isn't it? Yeah. Sulfur has a paired number of electrons on its outermost shell, so it causes electron shielding. Not electron shielding, electron repulsion. Sorry, I'm really messing up my words. It causes electron repulsion, and that electron repulsion causes a decrease in ionization enthalpy for sulfur compared to phosphorus because it's unpaired, and therefore it's much easier to ionize and remove an electron on sulfur in comparison to phosphorus because of that electron repulsion, whereas the orbital in phosphorus doesn't have that. Sorry, it's been a long time since I've done it in organic chemistry, so but the point being is that the same. Now, if they ask you the same type of question, but for nitrogen and oxygen, right? It's the same type of. They're just trying to put you off by making you think that it's something different. It's the same thing, the same principle. Don't let it throw you off and think, oh, I don't know what to do here. I'm panicking. I'm shaking. Oh, I'm gonna lose my job. You're not gonna lose your job. You're not even employed. Maybe you are. Maybe you're not. But the point being is that I see a lot of people. They make mistakes. They don't actually. They don't. In general, they don't answer this question in relation to period 2, or anything to do with period 2 because they get scared and think I've never studied period 2. I don't know what's going on. Same principle as period 3. Just look down and say, if you're talking about lithium, beryllium, or anything you know about, or like from going magnesium to aluminium, you know there's a difference in energy ionization energy from magnesium to aluminium because you're changing the orbitals, right? Going from a you're going from a S to P. You're going from a low energy orbital to a higher energy orbital. I think that's the right terminology. Yes. There's decrease. But either way, that's the point being is I don't know. I don't remember the period 3 as much as I haven't done inorganic chemistry in quite a long time. But I know there's a difference between the ionization enthalpy going from magnesium all the way up until aluminium, right? And if they ask that question in relation, the point being is that if they if they ask that same question in relation to beryllium and boron, you treat that as the exact same thing as going from magnesium to aluminium. I just wanted to clear that up because I see a lot of people make that mistake. I see a lot of people make that mistake, and there's absolutely no reason why you should be making that type of mistake. And that's it. So now I'm going to go through some of the reactions with these period 3 elements with water, and then I'll go through the period 3 oxides. So reactions with sodium with water. So that's the reaction there. 2 sodiums plus 2 waters goes to form 2 sodium hydroxides plus water. And remember the state symbols. Now it's very important because you can lose a mark on some of these questions, and if it's a 1-mark question, you get no marks from it. If they specify that they want the state symbol, you don't do it. So I just do it anyway. I'm very good at just making sure to read the question. Again, I've done my exam, so keep that in mind. But you don't lose any marks if you've put down the state symbols and they didn't ask for it. They can't knock. They don't. So if you forget sometimes to check, sometimes it's just not necessary. And there's some questions when you do. Again, if you do more exam questions, you get more experience in seeing that there's some questions where they just don't ask for. You see, there's a pattern where there's some types of questions where they don't really ask for you to put down the state symbols, but some of them may do. But if you're not certain about it and you're the type of person to forget about something like that, you don't lose any marks for writing down the state symbol, unless your state symbol is completely wrong. and like you write something that's completely different, then yeah, maybe don't do that. But if you know water's always going to be liquid, right? So in most 99% of chance it's going to be represented as liquid. You don't lose any marks for writing things like that down. Now the reaction with sodium with water is a very vigorous reaction with cold water, and that's something that you need to be aware of, and you should know that from key stage 5, key stage 3 really. Either way, from secondary school, from GCSE, you know that reaction with water with sodium is a very vigorous reaction, and it's clearly very highly basic, because we know from when we did acids and bases that sodium hydroxide is a very very basic compound. It very strongly dissociates. It very strongly dissociates hydroxide ions in solution. There you go. That's what I was thinking of. There you go. Right, and you should when sodium is reacting with water, it usually does it. I think it fizz definitely. There's definitely effervescence because there's hydrogen gas there. Was there a flame? Where's in the periodic table? I do believe there's a bit of a flame, not as vigorous as probably as potassium and rubidium, but there's a bit of a flame there. Now, the reactions with magnesium with water. Now, reactions with magnesium with water is a much slower reaction in cold water. But that's the formula there. Mg plus 2H2O goes for magnesium hydroxide plus H2. Again, that's the state. Remember state symbols. Now, this reaction is very slow, but the reaction with magnesium, emphasis on the word cold water here, because the reaction with magnesium with steam, i.e., you know, H2O gas, and if they ever ask you to write the states to write the reaction with Mg with steam, it's very important that you represent H2O as a gas, because otherwise it's not the same type of reaction. But magnesium with steam actually forms magnesium oxide, which is different to what you'd expect with cold water, right? So magnesium plus water goes to form magnesium oxide plus H2. And if you react magnesium with steam, you get a magnesium oxide, and it's a much more vigorous reaction. And it makes the magnesium burn with a white light. And these are things that I'm saying all these things because when you answer the question, these are the key things that they're looking for. You get a mark for writing the right equation. If you need to balance it, they probably get another mark for it. But sometimes it'd be 1 mark for the equation and it being balanced. Another mark if they ask for state symbols, and then another mark for your explanation of what type of they may ask for what explaining or describe. They're not explaining, describing the reaction. It's saying that it's a vigorous reaction. It burns with a white light and it forms a white solid. And these are things that you'd expect from the reaction. So that's why I'm emphasizing on those specific points there. Now the reaction with sodium and water. Now the reaction with between sodium and water can be well understood by doing the reaction and adding the indicator phenolphthalein to water. So because remember we said that this reaction is highly basic because it forms sodium hydroxide, so you can just observe it directly, but there are other ways to observe this reaction and to see that it's gone to completion, and that's just by showing that we know it's basic. So if we get phenolphthalein, it will go from being going from colorless to pink or violet. So is the way that the way they like to describe it, right? Now, you'd expect effervescence, but the reaction to be vigorous, as shown by the speed at which the piece of metal moves at. I'll show you a picture of it below here, but we see effervescence as the metal moves around, and this suggests that a gas is given off. So the reason if you've ever seen this reaction from GCSE, we're dropping the sodium metal into some water, and it kind of fizzes around, and that's because it's emitting H2O gas, and that's just causing that little forwards motion, the forwards trajectory or that moving direction, and causing it to fizz around. And that's just to emphasize that there's effervescence of H2 gas as it's forming sodium hydroxide and H2 gas, and it's also and the way that it's moving is showing that it's a very vigorous reaction because it's always kind of fizzing around. But one thing that's very important to understand is that the reaction gives a basic product, and this is shown by a pink trail, right? shown by pink trail formed by the moving metal. And what do I mean by this? I'll show you what I mean by here. So the trail is pink since the indicator turns pink in basic conditions. So I'll come back to this here, right? So this is what I mean by here, where you have our we have water and we have phenolphthalein indicator in this water. That's going to be originally colorless with water, so that's not going to the color of the indicator in a neutral pH doesn't disrupt the color, because phenolphthalein in a pH of 7 is going to be colorless as well, so that's going to be fine. And if we add sodium hydroxide into this, we know, because it forms sodium hydroxide. If we add sodium to the water with the indicator phenolphthalein, we know that it forms sodium hydroxide solution, and therefore it's going to give off that it's as the metal fizzes around, it's going to form, it's going to cause the phenolphthalein to undergo color change from colorless to pink, to indicate that sodium hydroxide is being formed. And we can see that here. I'm going to use a let's go for green here, right? Where this is actually the metal here, and metal here. And as you can see, it's as it's fizzing around. This is just a little picture frame, a freeze frame, but it was fizzing around, and it caused this little, it probably went to all the way down here actually. Something like that. Probably went like that. The point being is that you can clearly see from here, it's probably this one right here, wasn't it? But it's causing the color change as it's fizzing around, showing that we're forming our sodium hydroxide here. Now, the trail is pink. The trail is pink since indicator turns pink in basic conditions. So this clearly shows the basic product being released as soon as the metal reacts. Now the product is, we have the gaseous product is H2O, which is causing the effervescence, causing it to really fizz around as much. And the basic product is sodium hydroxide, also represented as being aqueous, because it is aqueous, it's dissolved in water. And the reaction is 2 Na plus 2H2O goes from 2 sodium hydroxide plus H2. And then the end point of this reaction is represented here as this kind of like the whole thing will be almost pink, and we've got this massive blob here. That's the sodium now is kind of like blobbing up. It's forming just like a little ball. It's not I wouldn't say there's much of a flame with sodium, but it definitely shows it's a massive ball, and that's one of the things that they say in GCSE. Now, the things you don't have to talk about the forming of a ball as much, because that's not really a thing that they like to talk about. But the thing I was talking about with the effervescence of gas, the rigorous reaction, and if you put it if you dissolve phenolphthalein solution into the water, you put that sodium in, you'll see a pink trail showing that a basic product is being formed, right? Or color change from colors to pink. Now, reactions of the third period with oxygen, right? So I've gone through the period 3 elements. Now I'm going to go through period 3 oxides. I've focused on mostly 2, sodium and magnesium, because they're the ones that count the most. But now I'm going to go for that for when it comes down to water. But when it comes down to oxides, you're going to need to know much more. And if I don't think I've gone through every single one of them here, at least Seneca doesn't go through them. I can go through more of them if they don't turn up. I think there's going to be a part 2 to this video where I'll go through the other oxides. There's more than this. You do need to know more oxides than this, but it's just 3 of them, right? So the elements of the third period have distinctive and different reactions with oxygen. So sodium, magnesium, aluminium, and oxide. So the equations are 4Na plus O2 goes to form 2Na2O. Now if you write this as the if you decide to do 2Na plus half O2 goes to form Na2O, you won't lose the mark. They allow multiples, so you won't lose the mark. But this is just one way of doing it, without doing as much fractions, right? So 2Mg plus O2 goes to form 2MgO. Again, if you wrote Mg plus O2, you wouldn't, and to form MgO, you wouldn't lose a mark. But I suggest probably writing it as the full way, just saying that there. And also they're all white solids. I've double checked them on Google at least that they are white solids. Funny, 4Al plus 3O2 goes from Al2O3. And if this one is hard for you, if you're finding it difficult to understand why it's Al2O3, just remember the ratio. Remember the ratio. Remember Al is on, aluminium is on group 3, so it forms A. It forms an Al3 plus, and you have oxygen, or is this the O2 dissociates into an O2 minus, right? So it's you have a O2 minus. Now we need to get them to have the same negative charge and the same positive charge. That makes any sense. So here, what can we do to make them the same number? We can, well, the common multiple here is a 6, right? So times this by 2 to get 6, times that by 2 to get 2Al3 plus, which is essentially a 6 plus charge here, and times this by 3 to get 3O2 minus, which is a 6 minus charge. Opposites attract. Now we have Al2O3, and that's how I have aluminium oxide right there. Now the common features that these metals form their normal ions, so Na plus, Mg2 plus, and Al3 plus. And to work out the equations, you just have to balance the overall charge with oxide ions, as I've already explained. Tottenham were actually beating Brighton. So I thought Brighton could win that match. Anyway, it doesn't matter right now. Silicon and phosphorus oxides. These, now, again, I'll be going through more of it in more detail in other videos, but silicon and phosphorus oxides, these oxides are covalent materials. The reactions for their formation are silicon plus O2 goes from silicon, it's more like silicon dioxide, isn't it really? LSiO2. Now this forms a yellowish solid, and it depends on I've researched it, and the color is dependent on the concentration of the silicon and oxygen, but for AQA, yellow is the correct way of representing silicon dioxide, but I'm pretty certain it is, but check with your teacher if it's not. The color you can always research by itself, but understanding how to balance that equation. Now, silicon, I'm gonna make for one thing very, very clear. Where I'll go through it in the next video that I go through, but this is a very, very strong compound, and it's very important that you understand why it's a strong compound, and being able to explain why is very, very important. So, just good to know that is, and the type of structure that it is. I'll go through that in another video, but I've kind of hinted that it's going to be something to do with this here. The next one is phosphorus plus oxygen. P4 plus 5O2 goes from P4O10. Now I've represented it by P4 because that's how phosphorus is in its natural state. It's 4 phosphoruses, and silicon is actually Si8. So if you see Si8 plus 8O2, just know that that's because silicon is represented in silicon is usually by itself is in its kind of compound in 8, right? Represented by 8 silicons as a molecule. Now both these get the oxidation state of their group as phosphorus is +5 and in group 5, silicon is +4 and in group 4. Now sulfur is the odd one out in terms of the fact that it has multiple oxidation states. So sulfur can form multiple oxidation states, and it's the most common there's two main, there's multiple types of molecules of sulfur, but the most common are sulfur dioxide and sulfur trioxide. So sulfur dioxide, sulfur trioxide. And now the equation for the formation, sulfur by itself is S8, so Si8 and S8. So S8 plus 8O2 goes from 8SO2, and sulfur trioxide is made from sulfur dioxide, and that's using a catalyst. So to get sulfur dioxide, you can just do that with, I'm pretty sure you can just do that without a catalyst. But to get sulfur trioxide, you need to have sulfur dioxide react with oxygen under special conditions of roughly 450 degrees Celsius, 2 atmospheres of pressure, and a V2O5 catalyst to form 2SO3. Now this isn't a standard that you need to know that I'm aware of. I don't think they really ever asked that. You check with your teacher if they really care about it, but they never really, it's not like GCSE where they're really adamant that you have to know the temperature and that. You can probably get away with saying a high temperature, a high pressure. The one thing that I really they want you to know is that you have to use a catalyst for this. I don't remember them really. Is there a question you have to? I think there is. Yes, I think there is a reaction with We'll see later on with V2O5. There is a reaction with V2O5 acting as a catalyst for certain reactions, and I'll be going through again. This topic is quite a lot of content, even though it's quite a short topic. It's got quite a lot in it. You're learning about different types of catalysts and what actually happens in catalyst reactions, homogeneous, heterogeneous catalysts, and it's a lot to do with your understanding of oxidation states. But yeah, but this is it for this video. Again, emphasis on the fact that now I've highlighted I've highlighted the oxidation, the what's it called again, the state symbols for SO2, SO3, and P4O10, because now P4O10 in certain conditions can be represented as being a gas, and it can be represented being a solid. SO2 can also be represented as a solid, or can be represented as a SO3 is more likely to be represented as a solid than SO2, but SO3 can be represented as a solid or as a gas, and it depends on the different types of conditions that you're in. But apart from that, that's the end of this video. Hopefully you found it helpful. If you didn't find it helpful, please leave a comment in the video. And even if you did like the video, leave a comment. I'm just always trying to help out. And that's it.